Hello again, everybody. We're talking about section 3.3, and this is probably the most important section that we come through. We're going to have a lot of callbacks to this specific section, and we're going to write something very, very powerful during this section. It's not super important that you be able to recreate what I'm going to show you, but it is important that you understand the complexity of the operations that we're moving with. So let's just go ahead and jump into it. So we're going to talk about derivative rules, okay, which are the rules that are going to define finding some of these derivatives. Now, in previous sections, let me go to my laser pointer. Previous sections, what was our goal? Our goal was, hey, you give me a function and a point, and I can tell you the slope of the tangent line there. And as an example, if we just see a real quick sketch, of course, I like this line right here. Maybe choosing a different color. We identify this point. You had to give me the function and the point at the beginning. That means as soon as I change points, and maybe I want to go to point number 2, I have to redo that whole calculation. And so the idea is, what we want to do instead, maybe, create a new function we call f prime, okay, that we can plug in any point to find the value of the slope of the tangent line. So instead of it being, you give me the function and a point together, and I work on building that thing, now I'm going to create f prime of x as a function, and I'll plug in any points I want. Now, this means one limit calculation, but many tangent lines. It's just a more efficient way of doing things. Okay? So, here's what we need to talk about. Now, the very first thing that we need to talk about, and this is really important, and I would appreciate if you guys would write this down. Here is what we call the definition of the derivative. Okay? This is the definition of the derivative. F prime of x is what? It is a particular limit as h goes to 0 of the ratio f of x plus h minus f of x divided by h. There it is. That is, because this is so special, we're going to do our galaxy color. This is so special. This is the definition of the derivative. Every single thing that we do in this class that deals with derivatives ultimately falls back on this structure. Now, we're going to do a couple examples, and what you're going to find is this structure is tedious. So what most of this chapter is going to do is we're going to look for easier, better patterns. That's what the human brain is excellent at. Okay? But let's do an example where we actually use the definition. So let's say I define f of x to be 3x plus 4. Now, note, I hope you guys all know that f prime of x is 3. Because reminder, this has a constant slope. And if you know what the slope is, you know what the tangent line is. But we want to go back and we want to now use this definition. We want to see if we can come up with the same idea. So, there's f of x. Let's type in f prime of x. So, reminder, this is a limit as h approaches 0 of f of x plus h minus f of x divided by h. I always like to write the definition first. Let's change colors. So, what are we going to do blue to red? Well, first, we're just going to expand out what is f of x plus h. So, this is the limit as h approaches 0 of, well, plugging in x plus h here is going to be 3 times x plus h plus 4 minus f of x. And now reminder, when you subtract f of x, we're going to subtract the whole thing. So we're subtracting 3x, and we're also subtracting the 4. All this over h. Let's come back here. Now, we're going to expand out in purple we're going to expand out this 3x times 3 times x plus h term as 3x plus 3h plus 4 minus 3x minus 4. And just like the last time we took a look at these derivatives, something really important has happened. Notice I have a 3x term minus 3x gone, and I have a plus 4 term minus 4 term gone. Okay? So, this leaves me with the limit as h approaches 0 of 3h over h. And, once again, we have proof that h doesn't equal 0. That's what the limit tells me. H is approaching 0, but it never equals 0, which means I can divide h divided by h. And what are we left with? The limit as h approaches 0 of the number 3, which just tells us 3. And that's exactly why we get f prime of x equals 3. Again, something we knew, something we knew, but I just want to point out, this is the proof. This is showing me using the definition. Okay? So let's go a little bit tougher. Okay? I want to do one more example that's specific, and then we'll actually get to something kind of large. But I want you to get a feeling for how difficult these things really are. So let's do another f of x. Let's do something more complicated. Let's do f of x equals, let's do x squared plus 3x. Okay? Now, whenever you try to find these derivatives, I always think it's a good idea. One of the first things that you're going to need always is you're going to need this f of x plus h term. I like to find these at the onset, especially as they get a little bit more complicated. So, reminder, x plus h is x squared plus 2xh plus h squared. Distributing out the 3, we get 3x plus 3h. And we're just going to remember that, and we're going to use that. Okay, so let's find f prime of x. Notice, I don't know not a constant slope anymore, right? This is a parabola. Its slope is different. So I don't know what the answer is, but hopefully if I work out the definition of the derivative, I'll be able to find the answer. So this is the limit as h approaches 0 of f of x plus h minus f of x divided by h. All right. Now, I'm going to plug in this for f of x plus h and this for f of x, and we're going to see what we get. So this is the limit as h approaches 0. Make sure to give yourself lots of room. This is going to be x, This is going to be, get rid of that blue line, please. Haha. This is going to be the limit of h approaching 0, x squared plus 2xh plus h squared plus 3x plus 3h. That's just the first term, f of x plus h. Let's also plug in f of x, which, of course, x squared plus 3x. But a reminder, we are subtracting. We are minusing this whole thing. So not only are we going to have a minus x squared, we're also going to have a minus 3x. That's the number one mistake I see students make, is they forget that you need to subtract the whole thing. Now, just like last time, something very special happens. And this is something you should come to expect. And if it doesn't happen, you might have made a mistake. But notice, we have a minus x squared and a positive x squared. Gone. And we have a positive 3x and a minus 3x. Gone. And everything else that appears has an h. So I'm going to pull out that h on top from each of them. So 2xh just goes to 2x. The h squared goes to h. And the 3h goes to 3. Don't forget, there's an h on bottom. And, as a reminder, this tells me h does not equal 0, which means the h on top and the h on bottom cancel, leaving me with the limit as h approaches 0 of 2x plus h plus 3. Now, once we are here, this is continuous in that I can just plug in directly. Whenever you get rid of the denominator, typically that means that now we're just ready to plug in. So this is 2x plus 0 plus 3, or final answer, 2x plus 3. For f of x equals x squared plus 3x, f prime of x is 2x plus 3. And that is absolutely true. Now, you should be comfortable, in a Calculus 1 class, you should be comfortable using this definition. But as human beings, we're very in tune with the idea of looking at patterns. And it turns out there are some patterns that we can utilize to make these calculations just a little bit faster. Okay? So, let's talk about what some of those patterns are. And typically, we call these rules. Now, depending on what sources you look at, our text, my lecture notes, a different textbook, different lecture notes, you're going to have different rule names and different rule orders. Ultimately, they're all the same, but I don't want you to get confused about them. I get a little bit more detail into these rules than probably most other instructors, but we're just going to talk about these rules. These are going to hopefully speed us up. So, first rule we're going to talk about, I actually call it Rule 0, is the definition. And just to remind ourselves, f prime of x equals the limit, as h approaches 0, of f of x plus h minus f of x divided by h. That's rule number 0. And it's the rule number 0 because it's the definition. All of these rules are consequences of this definition. In some of them, I'll show you how that calculation comes out. And some of them, I'll show you if you want. You can email me and I'll provide that. But typically, I don't go through every single rule. Okay, our first rule is what we call the sum and difference. Okay? Now, one more aside note. If I am telling you to take a derivative, what is the notation? You know, we use plus to imply adding. We use subtracting or a minus sign to imply subtraction. We have multiplication, division, really more of a fraction. The question is, what does it look like? So, we're going to come back to these rules, I promise. But as a quick aside, actually I'm going to go over here. What are we going to use? Well, as a reminder, slope is y2 minus y1 over x2 minus x1, which we can use this delta notation, these little triangles, and they imply what we call discrete change. If we take the limit as delta x goes to 0 of delta y over delta x, so this stops being a discrete change, an average change, and starts being an instantaneous rate of change, we change those deltas to lowercase d's, which still implies change, but now it implies a continuous change. Okay? Get out of here. So, the notation is d over dx of something. Let's call it f of x. Taking the derivative with respect to x, that's what we call f prime. So this symbol right here are instructions to take a derivative. And really, it's instructions to start using these rules. So, first rule, sum and difference. As it turns out, it's very easy to find derivatives if your function is made up of the sum and difference of other functions. And here's what I mean by that. So let's let h of x equal f of x plus or minus g of x. And the reason I'm using plus or minus is I'm just saying this rule works for both adding or subtracting. You do have to choose, but if you want to take the derivative of h of x, well, and let me write it this way. So what would h prime of x be? Well, it would be the act of taking a derivative on f of x plus or minus g of x, and you can distribute this derivative operator, and you just find the derivatives separately and add them and subtract them. Now please note, this only works for addition or subtraction, but it does work. Okay? So, anytime you have a function that is made up of the sum or the difference of other smaller functions, we can focus on the smaller functions individually and build up that larger function. Okay? Here's a second one. Let's take a derivative of a constant number c times f of x. Again, there are reasons for this that I can provide, or you can look at your textbook, but ultimately we get to pull out this constant, and we can say, just find the derivative of the function and multiply it by the constant. Okay? Now, these two rules right here should remind you about multiplication. And here's what I mean by that. 3 times x plus y, we distribute the 3 to 3x plus 3y. D over dx of f plus g is going to be d over dx of f plus d over dx of g. Again, we're just sort of distributing this derivative operator to both of these functions. These are constants and variables. These are operators and functions. But ultimately, the structure seems to be the same. Now, what about this one? What if we have 3x times 4? Well, we can switch the constants, and we can say that's going to be 3 on the outside, 4x on the inside. And that's exactly what we've done here. D over dx of 2 times f, pull out the 2 and bring in the dx, is 2 d over dx of f. So again, there's this relationship that seems to be this adding subtraction sort of idea. Okay. Now those are all well and good, and there's at least one example that I want to look at in your homework that deals with this. I think it's question number 4. I thought this was a really, really good question, which is why I assigned it. Okay. It says, let h of x equal 2 times f of x and 4 times g of x, where the graphs of f and g are shown in the figure to the left. And the question is, find h prime of 1. Okay? I want to go back here real quick, and I'm going to go to the side so I don't mess up my rule list. Okay? So, I want to find h of x equals 2 times f of x. Was it plus? I'm sorry, I should remember this. Plus 4 times g of x. Okay? And the question is, we want to find h prime of 1. Okay? How do we do so? Well, first, we're just going to try and find h prime of x, which is going to be the derivative operator on 2 times f of x plus 4 times g of x. We're going to distribute that d of x, and we're also going to pull out those 4's. And what can we write? So this is 2 times the derivative of f, which will be f prime of x, plus 4 times the derivative of g of x, which we'll just write g prime of x. Okay? Now, that's what h prime is going to be. It's going to be 2 times f prime plus 4 times g prime, based on these two rules. And so I'm giving you these rules. You can take these as granted. You don't have to prove to me that 2 plus 2 is 4. I take it for granted. In the same way, you can take these facts for granted. So the question is, what is h prime of 1? Well, let's plug in 2 times f prime of 1 plus 4 times g prime of 1. And as a reminder, what does this term represent? It is the slope of f at x equals 1. And what does this term equal, the g prime of 1? It's the slope of the tangent line of g at x equals 1. So how do we find those? Well, that's why they gave us this graph. So in red we have this g of x, and in blue we have this f of x. And notice they're linear functions, which means they have a constant slope. The rise over run looks like g of x excuse me, has a slope of negative 1. We go down 1 into the right 1, versus f of x has a slope of 2, up 2 over 1. So, f prime of 1, to me, looks like 2, and g prime of 1 looks like negative 1. Now we're just plugging in numbers. 4 minus 4. I found that h prime of 1 equals 0. And again, because h is built with these simpler functions f and g, and because I know the rules that relate simpler functions to their derivatives, I can find that example. And there's a couple other interesting examples that use this rule. Okay? Now, I will point out, all we're really doing right now is we're taking a look at graphs. We haven't really found anything. So I am now ready, and I'm going to go brand new. I'm ready to do a very important rule, sometimes called the power rule. Okay? And it has to do with the derivatives of x to the n. So I'm going to do this based on the definition of the derivative. But this is a little advanced. This is probably the first time that you've seen this. And so we need to talk about, because we know the definition is going to involve this x plus h term, we need to talk about what is x plus h to the power n. Okay? Now, there's a pattern that you can kind of see. So let's go x plus h to the 1. That's just going to be x plus h. X plus h squared, we know this. X squared plus 2xh plus h squared. X plus h cubed is x cubed plus 3x squared h plus 3xh squared plus h cubed. And one more, just to justify my use of this pattern. Now, this is a pattern that is well known. It's a little complicated where it comes from. Here's the important point. These are the things I want you to know. Notice, we always start and end with an x to the n and an h to the n. That's where we always start with. And the second thing I want you to notice is the x powers decrease while the h powers increase. So they go from 4, 3, 2, 1, 0 in terms of the powers of h. Sorry, in terms of the powers of x, but the powers of h go 0, 1, 2, 3, 4. So, what does that mean if I take x plus h to some unknown power n? Here's what I can tell you. It's going to look like this. There will be an x to the n. Just like there was an x to the 1, x to the 2, x to the 3, and x to the 4. There will also be an h to the n. Now, what else will there be? There will be an n, 4, 3, 2, 1, times x to 1 less power, times an h. And there will also be a bunch of terms with h to the power 2 or more. H to the power 2, h to the power 3, h to the power 4. It's going to increase all the way up to n. And it turns out this is all the information I need to properly demonstrate this rule. So I'm going to go to the definition. As a reminder, f of x is x to the n. What does the definition tell me is the derivative of f prime? So this is going to be the limit as h approaches 0 of x plus h to the n minus x to the n all over h. Now, I'm going to plug in what I know is definitely going to be there. There's definitely an x to the n. There's definitely an nx to the n minus 1 times h. Then, there's a bunch of terms that all involve h. Bunch. Now, don't forget, we must subtract an x to the n, and we'll divide the whole thing by h. I'm really trying to differentiate my h's and my n's. Okay, now, as we saw in every single case, x to the n minus x to the n cancels. So what are we left with? We're left with a bunch of stuff that includes h. So I'm going to take away one h from each of these. And I know that everything inside here contains h, because I know the powers of h are going to increase. It goes 0, 1, 2, 3, 4, all the way up to whatever n is. So I'm going to say it's the limit as h approaches 0 of h times, take away h, in x to the n minus 1, plus a bunch of things that still involve h, because they're at least h squared, plus an h to the n minus 1. And once again, we know that this piece right here, h, does not equal 0, which means I can cancel that and cancel that. And now I have something continuous that I'm just going to let h be 0. So this is n times x to the n minus 1 plus 0. Or, and this is really, really important, and I'm going to write this down as the rule. This is the power rule. Sorry for going away so fast, but I really want to write this rule down. This is, if I had to be honest, this is 90% of this class, is knowing this rule. The derivative of a power, x to the some unknown power n. We bring down the power and reduce it by 1. And I'm going to write those rules explicitly. We bring down the power and we reduce it by 1. Now, with just these three rules, you would not believe all of the different functions that we can find derivatives of. It really is quite amazing. So, let's talk about some. So, remember 3x plus 4? We can rewrite this. Reminder, there's an understood power of 1. Now, this constant term also has a power. It's just x to the 0. So, what is f prime of x? Well, it's d over dx times 3x to the 1 plus 4x to the 0. And as a reminder, we can bring this inside these d by dx's, and we can write this is 3 times d over dx of x to the 1 plus 4 times d over dx of x to the 0, using the first two rules. Now, using the third rule, what are we going to do? remember what our rules are. I'm just going to go over here real quick. Bring down the power, reduce it by 1. Bring down the power and reduce it by 1. Bring down the power and reduce it by 1. Now comes our cleanup. So, 3 times 1 times x to the 1 minus 1, well, that's 3 times x to the 0. And 4 times 0 is 0, or our answer is 3. Notice, we got the same answer we always knew was true. This was a linear function with a constant slope. And we were able to find it without directly using the definition. We used the definition to find the rule. So the rule is based on the definition, but we don't have to use the rule. This is like knowing the rule is that multiplying by 2 doubles something. Can you prove that to me? Yes. Which means you don't have to prove it to me every single day. If it was true yesterday, it's going to be true today. What was that second example that we used the definition on? X squared plus 3x. Guys, this is going to get so much faster. So, once again, f of x equals x squared plus 3x. The question is, what is f prime of x? So once again, we're going to take a derivative on x squared plus 3x. We're going to ignore the constants, and we're going to bring in that derivative operator. This is going to be the derivative of x squared plus 3 times the derivative of x. And as a reminder, I'm going to always write x to the 1. So keep in mind, what are our rules? We bring down the power and reduce it by 1. We bring down the power and reduce it by 1. This is going to be 2 times x, and this is going to be 3 times 1 is 3 times x to the 0. And as a reminder, x to the 0 is 1. Exactly what we found previous using the definition, but we didn't have to use that clunky, hard-to-find definition. Again, the definition builds the rule, and the rule is what becomes useful to us. Maybe I should zoom out. That might make it a little bit easier for you guys to see the context of things. Okay? This is called, let me go back to our list real quick. This is called the power rule. And it is a very powerful piece of the derivative notation. Okay. Now, I want to leave you with one very important concept. Let's talk about a function g of x, which is the cube root of x. So, reminder, anything that is written as, the bth root of x to the a, there's something called fractional notation. Okay? That's the same thing. The bth root of x to the a is the same thing as x to the power of a divided by b. And the point is, the rewrite is a power that we can use this rule on. So if g of x is the cube root of x, what is g prime of x? Well, that's going to be d over dx of the cube root of x. I'm going to always rewrite in terms of powers, which is going to be d over dx of x to the power 1/3. Now, does this rule state that n has to be an integer? No, it doesn't. We just have to follow the rules, bring down the power, and reduce it by 1. So, bring down the power and reduce it by 1. And what do we get? 1/3 times, you can think of 1/3 minus 1 as 1/3 minus 3/3, which comes out to be x to the power negative 2/3. Now, if you really want to rewrite this, or the negative tells me to reciprocate it, and the over 3 tells me to take a cube root, this is also 1/3 times the cube root of x squared. But I will point out, I like this better. But I will say, this thing is equivalent to that thing. But ultimately, I think this is a better result. So, what is section 3.3? We have our first 3 derivative rules, technically 4 if you count the 0th rule of the definition. We know that derivatives can get expanded across sum and differences. We know that it ignores constants. But we most importantly know if we can represent a function of powers, or as the sum or difference of constant powers, like a polynomial, we have an explicit rule to find the definition of the derivative without using the definition. That is what we want. Hopefully this helps you on section 3.3. Again, if you have questions on specific homework questions, or if there's something I said in this lecture that you would like to see more of, please, I am open and willing. All feedback, we can certainly get you what you need. Have a wonderful rest of your days.